Near the shores of a mid-Pacific island, a scientist inspects a wave recorder, which measures the pressure and direction of waves and tells him something about the distant winds that created them. In Southern California, an observer checks a tide gauge as part of an international study of tides, the rise and fall of the ocean level in response to the pull of the sun and the moon. Aboard a research vessel in the Philippines, a survey team charts the contours of the unseen landscape beneath the water. On a college campus in Texas, a scientist studies water samples from different parts of the Atlantic, seeking to add still a few more facts to our slowly growing knowledge of the seas.
The majesty and the mystery of the seas are inexhaustible. Immense in their extent, irresistible in their power, the seas have inspired men through all the ages with feelings of awe and mysticism and fear. No one can halt the tides or fight the currents or control the waves, but everywhere men feel a compulsion to pit their strength against the sea, to explore it, to wander about on it.
This compulsion, described in our own day by the Danish explorer Peter Freuchen, has drawn man.
Today, a new breed of man has taken up the challenge of the seas, the ocean-going research scientist. The oceanographer uses the knowledge and techniques of many different sciences to broaden his understanding of the seas. He may be a physicist or chemist, geologist, biologist, or specialist in more than one field. He must be at least part meteorologist to probe the complex interaction between the oceans and the atmosphere. For the oceans are a great balance wheel of climate. They absorb and store the heat of the sun and moderate temperatures along their shores. From the oceans comes most of the moisture in the atmosphere, nourishing the clouds that give us rain and snow. But sooner or later, by one means or another, most of the moisture in the atmosphere finds its way back to the oceans, from which it originally came. This cycle, in turn, is linked to the complicated circulation pattern of the seas. For thousands of years, men sailed with the wind, depending upon breezes to move them. Only in recent centuries did sailors on the North Atlantic come to realize that the surface water itself was moving. Men had discovered the Gulf Stream, and Benjamin Franklin published a chart of it in 1769.
Since then, mariners and scientists have located the main surface currents in the oceans of the world. In the northern hemisphere, they move in large clockwise patterns. In the southern hemisphere, their motion is counterclockwise. Although influenced by temperature changes and the Earth's rotation, these currents are strongly controlled by the major wind systems of the atmosphere. The trade winds in the tropics, the westerlies in temperate zones. This is a greatly simplified picture of ocean and atmospheric circulation. Actually, there are many unsolved problems and unanswered questions which continue to draw the oceanographer back to the sea.
Instrument, the bathythermograph, makes some of this work easier. It is highly sensitive to temperature changes, which it records on a small glass slide. One of its big advantages is that it does the job while the ship is moving. One of its limitations is that it can be used only to depths of about 900 feet. Nevertheless, from these slides, useful temperature profiles of the ocean are being made. Measurements like these have already produced new concepts of currents in the North Atlantic.
For example, a map of the Gulf Stream today looks very different from the one published by Franklin. It shows many separate currents, some of which break off, meander, and even reverse themselves. The course of the entire stream has been seen to shift as much as 100 miles in a week.
Observations at sea are closely linked to experiments ashore. With models of continents and oceans, a physicist tries to duplicate the forces that create surface currents in nature. Colored inks and dyes are added to make the flow patterns visible. The rotation of the Earth and the action of the winds are simulated in the laboratory. Through time-lapse photography, some experiments show how currents might be driven by these forces and shaped by barriers of land.
But theories must fit the facts. Insights gained from laboratory experiments must be tested in nature.
The laboratory of nature for the oceanographer covers almost 3/4 of the Earth to depths of more than 6 miles. All over the world, the basic instrument for studying ocean waters in depth is the Nansen bottle. A score of these bottles with attached thermometers can be hung on a single cable and lowered to any depth. A small weight trips the bottle, fixes the temperature reading, and releases another weight to the bottle below. The entire string of bottles brings back samples of water collected at various levels, between the surface and the bottom. They go first to shipboard laboratories for analysis. These small samples help the hydrographer piece together a picture of the complex circulation systems in the vast length and depth of the oceans. For to him, differences in temperature and salt content mean differences in density or relative weight. And profiles of such density differences reveal the movement of water masses, horizontally or vertically. One technique for tracing these movements utilizes a 50-gallon drum to bring up large samples of water from the very bottom. From such samples, a geochemist can extract enough carbon-14 to determine when this water was last in contact with the atmosphere at the surface. From the constant continuing analysis of new data, oceanographers try to understand how the various currents are interrelated. In working out one theory of overall ocean circulation, a scientist reasoned that there should be a deep current in the eastern Atlantic running beneath the Gulf Stream and in the opposite direction. A remarkably simple research tool, the swallow float, made it possible to test this theory. It is a cylinder which can be set to float at any desired depth. A sound transmitter, or pinger, is enclosed in one end. The instrument is dropped into the Gulf Stream and tracked by its sound signal.
Pingers dropped to depths of less than a mile drift northeast with the Gulf Stream. Floats dropped to middle depths remain almost stationary. But those dropped near the bottom drift southwest, proving that a deep countercurrent does exist nearly 2 miles below the surface waters of the Gulf Stream.
Of all the countless creatures of the 7 seas, none is more vital than that strange community of floating plants and minuscule animals called plankton. Highly magnified, a strange world of fantastic creatures is revealed to the biologist. Most important of the microscopic plants is the diatom, the grass of the sea, the basic food of marine life. Most minute sea animals feed on diatoms. These are eaten by small fish, which in turn are eaten by larger ones. The ocean explorer of today has come a long way from the glass barrel excursion of Alexander the Great. But for the most part, man himself is still confined to shallow waters where sunlight filters through. To the deeper and darker regions, the scientist sends his instruments, extensions of his eyes, ears, and hands. A trawl bag dragged over the ocean floor collects samples from the cold, dark depths. Among the specimens found by marine biologists is a small living mollusk belonging to a group believed extinct for 300 million years. The underwater camera brings the scientist glimpses of things his own eyes cannot see. It also brings evidence of abundant life in deep water, a fact long disputed before such proof was available.
This shrimp, 5 inches long, posed for its picture 2,100 feet below the surface of the Mediterranean. In the Atlantic, the camera caught a sea spider and some brittle stars at 6,000 feet, a sea cucumber at 8,500. No less interesting to the marine geologist are pictures of the ocean floor itself. Ripples give visual proof of currents along the very bottom. And manganese nodules, $500,000 worth per square mile, hint at fabulous mineral reserves which may one day be tapped.
The underwater camera gives few scattered glimpses of the vast ocean bottom. For an actual continuous profile of a landscape over which a research ship is moving, he uses the precision echo sounder. A transmitter directs a sound pulse toward the bottom. A receiver picks up the echo as it bounces back. The intervals of time between pulses and echoes are converted into distance to reveal the varying contours beneath the ship. From soundings made all over the world, more complete pictures and models of the ocean bottom are emerging.
They reveal great mountain ranges similar to those on the continents, trenches several times deeper than the Grand Canyon, as well as plains flatter than any on dry land.
But the deepest waters of the ocean are not the end of the oceanographer's quest. The geologist wants to know what the bottom itself is made of, and even what lies beneath it. Explosion seismology helps him answer these questions. Two ships are generally used, one to drop the explosive charges, the other to record seismic waves.
KIBR, this is KSLF, on the air for shot 987. A 300-pound shot, 31-inch fuse. Take it in 30 seconds. Light the fuse!
Seismic records help the scientist penetrate to the Earth's crust. Other instruments take him even deeper. The magnetometer can make a continuous record of the Earth's magnetic field while being towed behind a research vessel. Measurements of magnetism and gravity at sea, combined with echo soundings, give the marine geologist important clues to the structure of the Earth's crust.
Thus, from a research ship on the surface, the oceanographer reconstructs an amazing picture of the world beneath him. The circulation of the waters in the depths, at the bottom. The contours of the bottom, the layers of sediment below, and the Earth's crust underneath. Between the crust and the ocean bottom, in the sediment, are deposited the accumulated records of life on Earth, going back perhaps 1 billion years. These records, mixed with vital traces of Earth history, are far better preserved beneath the oceans than on continents exposed to sun and ice, wind and rain.
To obtain samples of sediment, a long coring tube is lowered to the bottom. There, a heavy weight drives it into the mud. This pipe penetrates the bottom to depths as great as 80 feet and cuts out cores that may go back millions of years. The cores are carefully forced out of the pipes and cut up for easier handling. Samples are taken for shipboard examination, but full-scale analysis requires the facilities of a land-based laboratory. Like the pages of a history book, the cores reveal the mysterious language in which nature records events. Different colors, textures, layers and substances hold traces of the evolution of life, of drastic changes in climate, of the appearance and disappearance of great land masses, long before man appeared on Earth. Each page of the history book must be deciphered, line by line. Lengths of cores are filed, like reference books in a library, for future study. The top 2 inches of this core hold sediments deposited during the past 2,000 years. Section is only a small part of the original 80-foot length. There are hundreds and hundreds of cores to be examined, but from the fragments already deciphered have come astonishing results.
In one group of cores, warm water fossils were found in a layer directly on top of cold water fossils. These observations led to a new theory of ice ages, suggesting that they may begin and end in a few years or decades, rather than centuries or millennia. In other cores, layers of sand were found mixed with clay. Further study eventually showed that massive currents of sand and mud flow along the ocean floor. In still other cores, a thick layer of white ash marks perhaps one of the greatest volcanic eruptions ever known on Earth, 60 to 80,000 years ago.
Deciphering such cores with their dramatic revelations of the past brings the oceanographer still a little closer to his goal. But exploring the vast masses of restless waters, which rise and fall with the tides, are driven by the winds, circle, sink, and surge anew, this is a truly monumental undertaking. Still, men will continue to explore the seas, as they have since earliest times. Not only because the seas exert their influence on all the domains of life, but also, perhaps, just because they are there. Men will learn more about themselves and the planet Earth as they respond to the challenge of the oceans.